One of the most fundamental concept of geometrifying trigonometry is all numbers are triangles and all triangles are numbers. How? Obviously, the numbers, real numbers, are of two types: rational numbers and irrational numbers. Rational numbers mean there are the ratio. Ratio means something is there in numerator and something is there in denominator. Irrational numbers are approximately rational numbers, because if we take up to 3 decimal place, 6 decimal place, 30 decimal place, in CAD we used to do with the 60 decimal place, and sometimes in Boost we can handle with the big float, that is 128 decimal places. But how long? We are not going to bother up to 3000 decimal place or 3 crore decimal places in our practical life. Practically we are satisfied up to 30 decimal places. No one is bothered in real world to handle with more than 30 decimal places in regular use. 3 decimal places more than sufficient for daily use. So irrational numbers are also actually ratio of some approximate numerator and approximate denominator. Okay, that's it. So every number is practically a ratio of a numerator and a denominator. Now what triangle is? And triangle is a shape where there are 3 line segments and it encloses a shape. In trigonometry, we know the name of the line segments, that is hypotenuse, base and perpendicular, and we have strict ourselves with a 90 degree is always involved. We are generalizing it to any kind of angles are possible in the triangle. Now triangle has 3 sides. One is the input side. One line is already given and another line is constructed, and when a second line is constructed, the third line is also constructed in the byproduct. In geometrifying trigonometry, 3 points also have a well-defined names, like the point where the least sized angle is formed is pivot point. The point where the largest size of angle formed, suppose 90 degree, it is the stretch point, and the third point is the nodal point, which can have any other values of angles, the enclosing angles between the sides. If we are modeling it as the classical trigonometry, then we can say the theta, the angle with which we are bothered, is the seed angle. The opposite of the seed angle are 2 number of angles, where one is 90 degree, the point is the stretch point, and other point is the nodal point. The pivot point, stretch point and nodal point, these are very much used in several theorems, because when we generate the automated locus or automated calculations of multiple trigonometry expressions, then we have seen that the nodal point of one triangle overlaps with the stretch point of some other point, other triangle. So several theorems are in there where these points are also involved, and that gives a large number of insights to our understanding. First of all, in trigonometry ratio, if we look at the trigonometry ratio, then we see cos theta is equal to base by hypotenuse. In real life, when we try to use cos theta, when we multiply anything with cos theta, what does that mean? That means a number which is the length of a line segment is multiplied with cos theta and we get another number. What we get actually, when a cos theta is multiplied, sometimes we say the group action, or sometimes we say it as a charging of cos theta on some number. Geometrifying trigonometry says it is not number. It says a line segment is given, suppose L is given, and we are charging cos theta on that line segment, and we are getting another line segment. How should we think in this condition? Here in the last we have shown that numerator divided by denominator means denominator is the length of a line segment which is given, or a line segment itself is given. Now we are charging a ratio on that. It has a group action, it has a geometry group action which generates the line segment whose length is numerator. If we think whole trigonometry in this way, then we can clarify the ratios of trigonometry, of classical trigonometry, very practically well useful. Suppose when we find a scenario in our height and distance problems, then students face a issue when to use cos theta, when to use sin theta, when not to use tan theta, or when to use tan theta. And I have been in this industry of practical application of bridge designs, truss design, girder design, and several kind of geometry are involved in CNC machines, manufacturing of the floors, automated manufacturing, and now AGTX systems are also coming, automated welding, automated cutting, automated girder fabrications are done, Woodman, Phi-shape, these kind of CNC systems are coming where the automated assembly lines are generating from the STL files and other NC systems, where I am telling about the AGTX, or Tekla has also brought several kind of automated production management systems. All the BIM industry are following in this way, automated transportation, loading, automated port management. These whole big things are all integrating with each other, and DXF is integrated with NC, IFC is integrated with NC. In this world, we have seen people face big issues when they face sec theta, cosec theta, cot theta. How? Sec theta, we should visualize it as when base of a triangle is given, of a right angle triangle is given, and we have to find the hypotenuse of the triangle, then we should charge sec theta. We will not tell it as a multiplying with sec theta, we will tell it the charge with sec theta on the given base, and you will get the hypotenuse. So in the similar way, when the perpendicular of any triangle is known or given, the line segment is given, then we can charge the geometry action of cosec theta, and we can generate the hypotenuse. And then if we end that join the lines with the nascent single valency points, then we will get the complement line segments. Similarly for cot theta, when we find that perpendicular is known but we have to construct the base, then we charge the geometry action, group action of cot theta, and that will construct two lines. One is the output line and another is the complement line. The output line is the base in that case for cot theta. When we are charging the perpendicular with cot theta, then we get the base of the triangle, and automatically the third line is assumed that it is also created, because we can easily construct a line between two given points, two generated points in that case. If we think whole ratios of trigonometry, of classical trigonometry, with this logic, with this reasoning, then we can think any number is represented as the rational fractions, that is the numerator divided by denominator, and division symbol in daily life is reinterpreted as a numerator divided by denominator, where denominator is the length of given line segment and numerator is the length of generated output line segment. Now denominator is a given line, numerator is a constructed line. Due to the group action of the number, the ratio, when a ratio is multiplied or charged on anything, then we assume that denominator is the given line segment, and after charging the ratio, the numerator line segment is generated. And when these two line segments are generated, obviously the one point of numerator is connected with one point of denominator, and another point of numerator line segment is free, another point of denominator line segment is free. Just join those two points and you will get the third line of the triangle, that is the complement line segment, automatically generated as per the construction protocol of geometrifying trigonometry. If we think every numerator by denominator in this logic, then we can prove our proposition here that all numbers are triangles and all triangles are representable as numbers, because the one is considered as the output line, another is considered as the input line, and the third line is auto constructed due to the process. In this way, if there are several ratios multiplied one after another, from our school days, that we can easily assume that one unity, that is one value 1, is on the leftmost side, and that is multiplied with n1 divided by d1, then it is multiplied with n2 divided by d2, then it is multiplied by n3 divided by d3. In this way the chained ratios are multiplied. If we think a problem like this, then in geometrifying trigonometry, that one, which we have written in the first, that is taken as the L, capital L, which is the given line segment whose length is 1. Okay, we assume this. Now this L is consumed by the denominator, and we make the align and scale to fit. In the previous videos, I am making the videos in order, such that if you see it in order, you will connect the whole thing easily. There, when I have shown the multiplication protocol in geometrifying trigonometry, there I have already said that how, and demonstrated also with the Geogebra file, that how align and scale to fit construction mechanism works. In the same way, when L is given, which is 1, just align and scale to fit the first ratio. Align the denominator of the first ratio to L and get the triangle where the numerator of the first ratio is the output. This numerator of the first ratio becomes the input for the second ratio. This input means now we will align and scale to fit the second ratio to the output line. I will show it in next videos stepwise. Here I am trying to explain the reasoning, how to think about this. So in the chain ratio, first L is drawn, a single line is drawn, which is a given line segment, say L. Now we align and scale to fit the first ratio's denominator with the given line, and automatically numerator is generated as a seed angle is formed. Then this numerator is the output. It is consumed as the denominator, that is the denominator of the next ratio. So next ratio is also a triangle which is aligned and scaled to fit with the output line. In this way we can continue any chained multiplication of different ratios. So n1 divided by d1 into n2 divided by d2 into n3 divided by d3. Ultimately the first denominator is the first input and last numerator is the final output, and we can place one point of the denominator of the first denominator is connected with the first point of the last numerator. Then two free points will be there. We will simply connect that and we will get a triangle. This is the way we can think of every numbers are representable as triangles and every triangles are represented as numbers. If we take any two line segments from any triangle and consider that one line is, out of these three lines, one line is the input line, any line from other two is the output line, then length of output line divided by length of input line is a ratio, and which is a number. This is the fundamental concept of multiplication and division in geometrifying trigonometry. Thank you. We will demonstrate these geometrically in next video.